All right, let me welcome everybody who has joined us in this meeting. With best greeting to Dr. Golnaz Habibi, a former student of K2C, a very prominent alumni of ARAS, who we have the pleasure having her talk in this meeting. Just a very short, brief introduction about Golnaz. Golnaz is currently a research scientist at the Department of Aeronautics and Astronautics at MIT. Previously, she was a robotics engineer at Autel Robotics, leading the team responsible for motion planning for autonomous drones. Golnaz received her BSc in Electrical and Control Engineering from K2C University and from Advanced Robotic Automated System ARAS in 2005, and her MSc in Control Engineering from Tarbiyat Modaris University, Tehran, Iran in 2007. And she obtained her PhD in Computer Science from Rice University, Houston, United States in 2015. Golnaz's work lies at the intersection of robotics, control, machine learning, and multi-agent systems. Her algorithmic solutions have been implemented on real robotic systems, and they have been applied to real-world problems such as autonomous driving, multi-agent, task allocation, and collective transport. Her current research focuses on visual autonomous navigation, a very, very important and interesting topic of research with reliable communication and improving the safety and reliability of autonomous agents. I'm sorry for being a bit longer than usual. Please, the floor is yours, Golnaz. You can start your presentation.
Hi everyone, and thanks so much, Dr. Takrat, for inviting me to this ARAS webinar. So I'm it's my pleasure to present my work and at the end summarize some of our work from our lab at MIT. This talk is more focused on safe and resilient autonomous navigation in highly dynamic environments. Recent progress in robotics and AI, based on that, actually, there are different category of the robotics applications. For example, on the first row, you see that Da Vinci robots in working on the surgical robotics or the Waymo robotics that for the autonomous driving systems. So, and also the other categories would be like, for example, other cases of like Scalable, the drones robots, or Kiva at Amazon or Boston Dynamics. So we can classify the robotics application in three different categories. The first one is saving the lives. For example, Da Vinci or Waymo for autonomous drivings or the surgical robotic systems. Or just robot, we use it for the entertainment, like Skydio, or for example, on the left side, on the middle, you see that they use like a sort of the drones for Olympic event. So it's just for the entertaining. And the last one is for a robot as a robot services, for example, Kiva, or in Amazon that for transporting different objects, or in Boston Dynamics that using the leg robot that can help the human in different services. However, numerous challenges still remain. The first one that I want to talk about today is about transferability. Assume that, for example, we have the robot in the ground robot, and in just like on the earth in some specific environments. So usually our robots are not adaptive to the environment or task, different from that what they executed. For example, if you want to have the robot to be transferred to the other environment, outer space, or robustness, the other issue. So for example, many of the neural network-based robotic systems are not robust to adversarial attack or uncertainty. For example, adding some adversarial patches to for example, this stop sign makes the robot have a mistake to recognize the stop sign to another sign. And the last one is intractability. as we have more robotic system in our real world, we need to consider the interaction between the robots and humans, as well as intelligent systems. For example, on the left side, you see that the robotic bit playing with the human or connected vehicles in autonomous driving systems. So today I'm talking about this, covering these three different fundamental robotic limitation and how I address it in my research. So the first one is the robustness and certifications. In the terms of the safe and robust learning, recent advances in neural network and learning-based methods leads to efficient algorithmic in robotic and navigation. But still they have some issues. For example, as I also mentioned earlier, adding like some presence of some adversarial attack make it that the neural network that not be robust. For example, on the right side, adding some specific noises to the images from the panda, it make it as a different, it classifies a different object. And the other problem is, for example, if the data distribution is different from the data that you learn from it, so it makes it that the model is not behaving well in the presence of the new data sets. And one other issue is the transferability. In many cases that because of the safety issue, we have to use a simulation for learning the robots, but now the question is that how we can transfer the learning model from the simulation to the real world. And this is very important, especially in the safety critical domain, for example, autonomous driving systems. You may have heard about some crashes at the United States, for example, from Uber self-driving cars that make it the self-driving car could not consider the pedestrians and kill the pedestrian. And also, for example, in this video, you see that on the right side, that very small stickers on the roads make the autonomous driving system think about that is a very large object and deviated from the original path, which is not safe. And on the left side actually is one of our a jackal robot in our lab, and this robot actually is running in our computer science department. And as you see that this robot is navigating different environments and trying to avoid the pedestrian-rich environment and by having the similar velocity as the human. But the other issue is that assume that if we have some uncertainty on the system and that we didn't consider during the training, how we can deal with in the other environment or transfer it to the new task. So the first one, I'm talking about why it's important and how we actually consider analyze the robustness of the system. And the problem set that we call is such a reachability set analysis. For example, on the left side, we have a closed loop system. So we have this drone that we want to, we have it in initial start point and we want to move to the goal state. Now the question is that how we can approximate the output of the drone such that we verify that the drone would be at the goal position, but always within a safe range. The problem is that usually the drone has some uncertainty on this behavior that makes it that not usually follow the blue path that we expected. So because of the uncertainty, there are some ranges of the uncertainty on the behavior of the drone or other autonomous systems. And that's usually more actually sensitive when we are controller is based on neural network. So the example of neural network in general is that, for example, we have input, for example, two-dimensional input x0, x1, and then we have some neural network that it gets that input x and also the theta of the parameter of the neural network and gives you some output here. And for example, output in two dimension. And the problem that we define is that given trained neural network and input with some uncertainty in a specific range, for example, here, this the rectangle, find a bound set of the neural network output, which is this type of the shape. So because we have a neural network and a lot of high dimensionality of the neural network usually, as well as the nonlinearity in different layers of the neural network, this shape should be usually very not very smooth, and also it's usually hard to find this output range and boundary exactly. So the challenge that we want to solve is actually it leads to a non-convex optimization problem, and it makes it very more computationally expensive and sometimes even NP-hard problem. And because of that, there are different algorithms comes to approximate this boundary. For example, this blue set, as for example, the boundary that we can approximate as some rectangle. And in general, we can say that there are a trade-off between the how it's fast and how it's exact. So our algorithm, we're trying to both be exact and fast, so we can have at least have a good approximation of the boundary, as well as to be fast as possible, but because we can run it on the real systematic robotic system. So the contribution that we have is that we combine the neural network relaxation method with a partitioning set, and which means that instead of just looking at all the input as an entire set, we partition the input and then estimate each of the partition, distribution of the output of each of the partition, and then the output would be union of all the estimated output. And then we refine outer output based on our algorithm. So this is an example. For example, you have an input, two dimension inputs. And actually the example here, for example, this robotic system, there's a writing system. So it uses like 2-gen robot systems. And then the question is that what's the output of this robot would be in terms of uncertainty in different dimension of the input. So the way that we do, we partition the input, we feed each in partition to the our estimator, we estimate the output, and the union of all the output of all this partition would be our output. So I show the example here. Our algorithm is called Greedy Sim Guided, or GSG in short, and you see that here by the black lines actually our algorithm output, and that's trying to approach to the red line, which is our approximation of the output from the Monte Carlo sampling. So the tighter to this boundary, make it our problem, our algorithm to be more less conservative and more efficient. And I will show you in one of the examples. So in general, uncertainty can come from the sensor noise or adversarial attacks, and the output of the system can be either we consider the worst case scenarios or just some base cases of the output, but in general, we can consider the boundary of the output would be given that input uncertainty. So the goal for now, we want to consider this type of the partitioning in certifiably robust deep reinforcement learning. And the goal is to analyze and learn policy and robustify the planning. What does it mean is that here we have a collision avoidance with the red adversarial attacks on blue agents position. And now I will show you the video here. So the things that you see in this video, the blue dots, actually for blue figures are adversarial attacks, try to hit the red one on the left side. So the red robot tries to avoid the collision with the blue one. So on the left side is a previous algorithm. And the previous algorithm, it doesn't consider that tight boundary for approximating the output or the estimation of the blue trajectory. So it is still safe, so it avoids the collision, but it's very conservative. In our algorithm, because we consider tighter boundary for approximating the output or the trajectory of the blue adversarial robot, so you see that the red one has more efficient paths, so it's both less conservative, but it's still safe. And so we show that the 22% our algorithm is faster time to go when we use our algorithm compared to the previous algorithm. So the next one, and the next topic I want to talk about is the transferability and lifelong learning. So if you have any question, you can take it now. Otherwise, I move on. Okay. So for the transfer learning, actually current artificial intelligence are very task specific and not generalizable to new domain or task. So we have two definitions, transfer learning and continual learning. Transfer learning means that we transfer knowledge across different tasks or domains, and continual learning also has a close meaning to the transfer learning. So if our model also has the capability of the transferability, it can also improve the learning and experience when it encounters new tasks or data. So this talk actually talks about and covered two different examples. One of them transfer learning and continual learning, and for the motion behaviors, in specifically how we can transfer our knowledge for learning the motion behavior of the pedestrians in highly dynamic environment. And then the other one is a continual learning, that means that how we can continually learn to improve the decision-making problems or planning problem, which is basically based on the reinforcement learning methods. So first of all, I'm talking about the transferability in pedestrian motion prediction. So many advances in object robotics occurred, but the problem is that most of them is not in prediction side. For example, you see that we have a tracking here, it's a combination of YOLO and sort tracking, and it track well the pedestrian environment, but because of the uncertainty, the pedestrian motion, they can abruptly change their directions, or even they stop their motion. And usually we don't know that pedestrian, what they have in their mind regarding their intention, as well as also the interaction of the pedestrians with the environment and the other pedestrians. It makes it more challenging. So specifically, you see in the road scenarios, in the autonomous driving systems, we have a lot of high interactions between the pedestrians, traffic light, even the context of the environment like crosswalks or intersections, geometry. So now the question is that how we can deal with this and approximate and predict the pedestrian behavior in the presence of this problems. And the other issue is that, for example, pedestrian usually doesn't follow the rules of the road and they don't stay in the road. So pedestrian, for example, can violate violate the rules easily. For example, they do the jaywalking. So our idea is to incorporate the transferable features to learn motion behaviors across different environments, for example, the intersections. As I said, that we want to learn the pedestrian behaviors at intersections, and the key idea is to use the different contexts in the environment. For example, the status of the pedestrian traffic light is one of the important contextual features, or the distance to the curbside, that's the other one. We want to, the prior work in this direction, that focusing on using the semantic map, but now we need to segment the environment first, and then we use that information for tracking the pedestrian or prediction of the pedestrians. Our contribution is that using a specific common coordinate frame. So I show you that in this picture. Assume that here is our intersections corner. Actually the origin of that intersection, or this coordinate is our intersection corner, and this blue is the position of the pedestrian. So we believe that the distance of the pedestrian and how it's far from the different the curve side of the pedestrian, it affects in its prediction. So, and its behavior and its next motion. So usually we measure the perpendicular distance, which is this black dashed line, but the blue line is the one that we use it, which is a contravariant distance. If you use this information, I mean this type of the distance, we can show that our model is able to transfer the trajectories to the new environment or new coordinate. So, which is actually, now we have a new feature which is invariant to the intersection geometry. I'll show you that in this example. For example, our goal is to consider that for example, the pedestrian in the red line, here. So both of the red line and also the purple line on the right side have the same intention, which is that crossing the road on the left side corner. So, but you see that the shape of the intersection really affects the pedestrian behaviors, make it that your trajectory is very different. So if you want to learn the model based on these two trajectories, you may fail because the appearance is very different. But if we use our new coordinate frame, all these two trajectories are mapped to the same trajectory shape or appearance, so make it actually invariant from the actually different intersection corners. So we use this model, so based on this the new features, so we have a transferable model, which is provided framework for comparing the learned model across different domain, or we can learn from different experiments. So, and actually this leads us to the new method that we call it similarity-based incremental learning algorithm, which is help us to having a model which is be able to incremental learning. As you know, many of the actually motion prediction algorithm is basically the one that based on motion data-driven models is limited to offline learning. So it means that you need all the data to train based on that. But our algorithm has this capability to continually learn based on the similarity between the motion primitives. And the idea is that first that we learn the dictionary learning from the trajectories. So we use the dictionary learning methods or sparse coding. So which means that our trajectories can be represented by a set of the motion primitives, mi trajectories tj. So I will show you in the one example how it means. So what this means that, for example, when we have a set of the trajectories here as a blue line, and we are at an intersection t time t0, so we use our model as a transferable learning model, and now the output is a set of the motion primitives, m1, m2 until m5, and then there's some transition because I'm t1, t2, t3. It means that this motion and these trajectories in the blue can be clustered to the small piece of the motion primitives, and also, of course, these motion primitives, they have some transition between them. So, I don't know what's that. So we can have a similar thing here. That assume that now we call it this is model M. Now we have a data model in time t1. So now we have a new data set is coming, and when the new data set is coming in t1, we just learn from this new data sets, and we learn a new model is motion M prime. And now the question is that how we can update our model based on these two models and coming up with a new model. So the way that we use a dual graph, then we fuse these two models. For fusing these two models, we define a specific node as a match node between two models. So we define some specific similarity measurement, and by using this similarity measurement, if the nodes from two different graphs have some similarity larger than some threshold, then we call it that these nodes are matched, otherwise they are not matched. So what happened is that the new model fused the matched models and matched nodes and also added the new nodes. So now we have this new graph, which is actually a fusion of these two graphs. And now we can continue and goes on with the other data sets. When the new data set is coming into T2, we can just continue this process and continue learning them up. So this is actually the approach that we tested in different environments. For example, at intersection scenarios, we collect our data sets with this, for example, a tripod with a LiDAR and 6 cameras, and it helps us to track the trajectories and track the pedestrians, and then use this information and also collect it in 5 different intersections. We use 4 of them for the training and the last one for the testing. So as you see that as the data from the left to right incrementally added to our model, our prediction error, which is the showing here is the AD, which is the average displacement error, which is the measurement between the ground truth and our predicted model, it decreases. And shows our algorithm successfully can learn continually and decrease the error of the prediction over the time as the new data is available. And also we tested on non-intersection scenarios, and we show that, for example, our algorithm, which is the blue one, has the best prediction compared to the other baseline to the yellow one, which is the ground truth. And just one point about all these data sets, we look at the trajectory of the pedestrians for 3.2 seconds, and then we predict for 4.8 seconds. So it's called a medium-term prediction. So I think we can actually use this model to consider and extend it for the multiple vehicles, because in Scylla we can fuse two models, pre-arbitrary model and new model. Now we have other part of the algorithm. I don't go to the detail, but I can refer to the paper that we have it, that how we can actually associate different models from the different vehicles, and then how they can fuse it together and come up with a new updated model that can be transferred to the different vehicles, and so they can update their models and they can indistributedly learn the model or collaboratively learn the motion behaviors. So the third topic is about intractability and multi-agent systems. We already talked about the multi-agent systems in the previous part, but I'm going to more focus on that in this part of the talk. Usually we see that the single agent has a great success in robotic application. However, in many applications, and especially realistic application, we need to also consider interaction between the multiple agents. So, for example, here we have the robotic soccer, or also which is like game-based actually applications, or we have like transportation, transporting the object, so which is actually the task that is more complex or difficult for the one object or one robotic system. And other cases, for example, self-driving cars, that we have fleet of the connected vehicles, and how we can collaborate, collaboratively learn also, and also control and plan based on the information that's shared between the vehicles. So now the other problem is that, as I said, the necessity of the human-robot interactions, so which is important. We also consider this interaction between the robots and the humans. So the key challenge here is like usually for the multi-agent systems, I can say is a part of it, but more important challenge that we have it like a scalability to large number of agents. So how we can have it as much as number of, for example, the cars or the agents that they can connect and collaborate the informations. And also because now we have a communication budget. Now the question is that how we have a more intelligent communicate to decide who or what to communicate among different agents. And the other aspect actually that how we can actually combine the learning and multi-agent systems together, which is now very active, is a very active research. But the problem now we have is that each agent usually also can simultaneously learning and over the time. And if we don't consider that the other agent are learning over time, we have the problem of the non-stationarity, and it makes the problem is more challenging. And the last part is that also, in general, they look at the multi-agent system in two different categories, centralized versus decentralized algorithm. So in this talk, this part, first I'm talking about, for example, here, I'm talking about the decentralized navigation. And for example, on centralized navigation here, we have a set of the and that we inspired by that, how we can collectively transport by a set of agents, that the agent can be very independent of each other, but they still can share some information. For example, here force feedback to collect and to move the object safely. And the other one also, I talk about some examples that we did for the centralized navigation. So I'm covering these two topics. So here actually for the centralized, one example here that Usually when we have a centralized approach, the problem is that there's scalability, because we need to control all the agents simultaneously, and usually we have a very high complexity. But our idea is that how we can use a massive uniform control. It means that we just use like uniform controls. We send it the same command to all the agents, but still we can get our desired result. This is a specific problem that, for example, for the position control, and we show that, for example, in this video, that only having one obstacle, as is a red obstacle, we can just move the other robotic agent with the same command, but we can create different, for example, shapes, for example, doing some formation control. For example, here, it's creating letter A. And here, for example, you see that we did the simulation. So we started with some area. We want to create eye shape, or even like smiley shape, or even, for example, Marcel as our logo for my Rice lab. And also here, for example, Mona Lisa. So different position control you can do just by running a single command and uniform command to others. And here's more general case that is, for example, just we have a light control. So you change the light on the left and right, and it's up and down. And then by having that, the agents that are sensitive to the light, they can react to this. And here's also on the kilobots from Harvard University, and we show that, for example, moving piano scenarios, that how we can use a kilorobots for moving that. So the other application here, for example, how we can cluster the robot agent. And here, for example, here is showing also for the 3D shape. For example, we want to make it this chair formation. So how we can use the 3D, again, using a uniform control to create that shape. And in the middle, so this is like a assembly problem that we can do it again with just a uniform control. Now I'm talking about the decentralized navigation, which is actually my PhD project, which is basically by a collective transport overview, which is the motivation is that the robotic, we want to build a robotic search and rescue team in an environment that is hazardous to the human being to be there, for example, earthquake, underwaters, or undergrounds, or the fire spots. And we want to, for example, save the injuries, so transporting some medical needs to them, or even transport them. That's our goal. And idea is that we want to use everything fully distributed, and all agents only have a limited sensing. They only have they don't have any GPS or Wi-Fi. They can use just the infrared sensors. So they have just local communication positioning, and we only have this decentralized execution. So our step is that first we explore the space by the triangulation algorithm. So we have a set of the robots, so they can explore the space, create the triangles network, and then using this connected network, so they can cover the environment without discommunication and disconnection with others. And then next step is that now they found the object and they attach object. So there are specific grid pairs that we design around the robots that they can, it's served by, actuated by servo motors, that they can attach the objects around the objects. But of course, this is like a toy example that our object has a specific knobs for, I think, a handle for the robot can attach it. But that's the idea for this attaching problem. So, and then when we attach the object, this manipulator robots around the object can distributedly find the width, different dimension of the object, and also the center of the object. I don't again go to the details, a lot of mathematical involved, but they do everything just using the limited information and local information, but they can find it by sharing the information with the other robots. They can find this information. And finally, we have a path planning. They create a path, and so the robots in the path can guide the other robots to move the object. And finally, we navigate the object. And based on that I did explain later that either they need to rotate the object to avoid the obstacles, or they just translate the object. For example, here the first one is rotate around the pivot. Here one rotate around the centroid that they estimate are already. So some point in the middle of the object, they try to rotate around that, or they do the translation around the object to the guide robot. So as I said, this is our robot that we built in our lab. It has 8 infrared receiver and transmitter, and also it has a radio antenna, and they have the gripper design for attaching the object. They can apply force individually on different points of the object, and also by using infrared sensors, they can measure the orientation of or heading of the other robots in their neighborhood as well as their distance. And based on that, we have two different task allocations. So we have a manipulator robots, just they manipulate the object and navigate around the different obstacles, and also the guide robot, just they create the path and they find the path so to be as a guidance for the manipulator robots to navigate the object safely. So for the path planning part, we have the environment like this. So we have a guide robot as a blue robots. I didn't show the manipulator robots, but manipulator robots also around the object. This is the object. For example, we want to move the object to the goal positions, and we have some obstacles as a black areas. And then this is actually based on each robot can measure the distance to the nearest wall, and then based on the distance, if the distance is less than the minimum dimension of the object, we call it unsafe. It means that this position is not safe to have object on that position. And safe minor, it means that there are distances between the min and max dimension. And it means that the object should be in a specific orientation to be safe to transport there. And the safe mean that our distance is higher than, is far enough so we can have object in any orientation when we navigate. And based on that, we have output that showing that it's basically the shortest path, and the shortest path here is among the robots as you see. And we use actually distributed Bell-Manford algorithm. It's very similar to digester, but in a distributed fashion. So, and the cost is here, but is how much we need to rotate and translate from one position to another position. And the idea is that actually, if you're familiar with the sampling-based algorithm, so or sampling-based path planning algorithm, we sample the environment by the robots, and also we have the like set of robots, and that can also identify that position is safe minor for the object, or is not. It's like safe for the object. So the white one is like unsafe robots, and the green one is are safe robots, and the gray one with the specific orientation, which is a safe orientation, it's a safe minor robots. Now the question is, okay, if we create a path, how we can navigate over the path? So because next step would be navigation. For doing that, actually, we have 4 different scenarios. Of course, we cannot have unsafe position, but based on each of them, for example, safe to safe navigation, we just do the translation. Safe to safe minor, because usually we need to go, it means that, or implies that we are going to narrow a corridor. We have to first rotate to be in a safe orientation and then translate. To safe minor to safe, we usually just translate. And if you have a safe minor to safe minor, we do both translation and rotation. So here just our algorithm is basically rotation around the pivot. For the rotation, either we do rotation around the one of the robot as a pivot, or rotation around the centroid. And for translation, we just do the flocking. So it's flocking to the goal position, to the guide robots. And we can have a combination of this translation and rotation. And this is also simulation showing that we use a Lloyd algorithm for covering the environment. So the robot start from the right side, entering the environment, find the object, some of them attach the object. That robots become the manipulator robots. So the others becomes the guidance robot. And after we have that, Now we have a set of, we measure the distance. We have the green, gray, and white robot as a safe and safe minor and unsafe robots. And then the tree is created, and the tree is routed from the go robots. And then we have the path, there's a blue one. Now the navigation starts. So the path is generated now. Here we want to guide or navigate the object and follow this path. Oops. So as you see that when the object is moving, so the other robots clean the environment. Again, based on the Lloyd navigation, they again cover the environment. So for any case, if the path is broken or if we need to regenerate the path, we have enough robot to cover the environment, have a connected network to create the path and replanning. And here showing the video, actually, we try to use the similar scenario that we would like in the future, that we have a human to want to transport the object. The blue robots are actually our guide robots, but as soon as the object approach that, they are going to be inactive, and then they just be in the environment, just avoid the collision with the object. And then it's rotated, it's needed sometimes, and then finally it can reach the goal. So I want to talk about the multi-agent learning part, strictly continual learning. So the idea is that we want to learn to additionally account for changes in other agent policies, because usually we have an issue that we don't consider that the other agents also learning over the time. So meta learning is a very active topic that they consider that they can learn to learn, or how we can improve the learning over the time. So now, actually, in our model, compared to the previous model, we added a new term, the meta learning, to consider the influence of the future of the other future policy of the other agent in the policy guarantee model that we usually use it for the reinforcement learning model. So this is actually showing that, for example, for the infinite present dilemma algorithm, I don't go to the, just one showing that the red one are algorithm, and the reward here is actually the max. We want to increase the reward, of course. So if you have a higher reward, it means a better learning model. So although the other algorithm, because they don't consider the other agents are learning, but our algorithm consider that our opponent in this game also is learning. So we have a better, in general, reward achieved. And this one may be more interesting. That this is for the competitive example, but for the cooperative example, as we consider a half cheetah problem. And then actually, this is video showing that this cheetah, the red part is controlled by one agent, and the blue one with the other agent. And this one showing that this cheetah gets the reward over the time, increasing the reward. If you look at the reward, values that it gets, it increases over the time as it's learned continuously. And it's showing that one of our examples that our algorithm successfully can train and learn this kid, for example, is increasing this reward to around 300. So we improve the player learning over the time. So, and also we consider the multi-agent learning in robotic gameplay. So you see that here, for example, two robots in the environment that we simulated environment that you try to play in the game, but usually the limitation of the prior work is that most of them doesn't have a much human-robot interaction game. So more focus on the, if there is, it's more like board game, not a physical game that you see here. And so our goal is that to design and implement a human-robot fencing game. So we can showing that one of the example of the competitive HRI example. So we have a sim-to-layer challenges in RL, also the reinforcement learning problem, which means that usually reinforcement learning problems, we are doing simulation for learning model. And now the question is that how we can transfer our model from the simulation to the real environment. So this one showing that, for example, the robots in the real environment, in simulation environment, they try to the one actually on the right side is try to protect the ball such that the one on the left side cannot hit the ball. So if the number of the hitting the ball from the left side makes it that it gets a score, the robot on the left side gets a score if hitting the bar more often. So also we show that using this type of the game, make it like there's a coaching problem. For example, because human can also learn from the robots in this specific game, that if they can learn from the robots. So actually that's what we did. Actually, we have the for example, human has a handle and this handle has the sensing that this can send information to the simulation environment or the robotic environment, and then this actually Vive. It's just actually either a visual reality headset or just the handle that sends this information, and we have some visual virtual ball here, and at the beginning we have some training episode that the human can learn that where is the ball is, and based on that we can have the reinforcement learning policy, and we can make a decision. So the robot can make a decision based on the information to get from the human. It tries this robot on the left side tries to avoid hitting the ball from the human. The number of the hitting the ball, if it increases, it means that the human gets more score. So I'm running here the algorithm and showing that actually different style of the game. So you see that human gets a different scores in the game. For example, this person wasn't playing very well, so his score is like -137. This is the other one. This is actually this project I did is from University of Washington. So they have a PR2 robots that they do different algorithm for the manipulation, and more focused their lab is more focused on the manipulators. So for example, this lady got larger, a higher number. This one, he was more trick on it, tried to. And it's interestingly that when we see that when robots play with different human style, also it's continual learn, so it improves over the time when it learns more policies and more different styles of the policy from the human. You see, for example, this guy got the better result. This one, the last one, is the best one. So I see that, you see that it's like it tries to some trick also on the robot to go on the other direction, and then suddenly it's just moving. And you see that 1037. Okay, cool. So, okay, I described some work from our project that we have done. So the question is, what's next? So we covered already that we have a transfer, the fundamental problem that we have it in robotic system, especially when we want to do the real world, the transferability, adaptability, and communication. And but the question is that when we have a robot more in the real world scenarios, still we have challenges in the area of the trusting to the robot, and also verification, how we can know that our robot really perform well or be safe in our situation, and also specifically for the neural network, the explainability, which is other issue that is usually the lack of this. So it's very important to be also consider all these factors and improve it. So for improving in general, that other thing that I'm going to talk about it a little bit in a few seconds, that how we can decrease the cost of the artificial intelligence, for example, using the vision-based navigation, and also safety and resilience of the human-robot in the environment interaction. I talk about it a little here, but still this part needs more improvement. For example, in autonomous driving scenarios, how we can consider the algorithm to be transferred in the different environments, and also different, for example, weather conditions here, how we can still have a good perception model. And of course, we need to have the robot in real world, so it needs to have a robot-human interaction. And we see that we already have, for example, Roomba robot as a vacuum cleaner, but having and reaching this type of the robot to help us in real world scenarios and challenges, still we need to work on that direction. And of course that we want to have a system to be more adaptive to interaction and learning. And the last thing is the scalability and heterogeneous multi-agent systems, because we are all like in a heterogeneous world, and we want to have a different robots with different capabilities, as well as having the agent the human agent as a part of this robotic system, how they can working together and still be resilient and efficient. So toward low-cost autonomous navigation, our goal is to reduce the cost of the autonomous driving by replacing the 3D lidars with vision or cameras or cheaper sensing. I showed a video here from our lab that it's focused on the cheaper, but it's not a vision yet, it's just a radar. So now the question is that, okay, we have this model and seems to successfully decrease the cost, but still we are looking for just a vision-based navigation to make it even cheaper. So, and we know that the vision compared this to the LiDAR have more information in terms of features, so it be just everything based on the visions. So based on the loop of the autonomous system, that we have a perception, planning, and control, how we can all this part based on the vision base. And usually, basically, we see that the vision base in the perception side, but definitely planning and control is also affected by the vision, and we can have the planning based on the perception-aware planning or the vision-aware planning or control side. So the part that we are working on it is for the multi-robot, multi-object tracking, but we want to just, for example, just molecular cameras, even no stereo cameras, just like single image, and how we can, based on the single image, we can still have a good multi-object tracking. Here's one of the autonomous driving scenarios in the Unreal simulation scenarios, and the goal is to detect the pedestrians or the cars in this environment and tracking them. I'm showing that here, for example, we have a group of pedestrians walking around, or that we have this car. So just using a single images here, just showing that just a 2D, but we also have the information of the 3D. So the output is also 3D bounding boxes. So this one showing just the 2D, but the goal is to showing that both 3D and 2D information, so based on just the image values. And also showing that two other videos is actually two other works from our lab. So just want to give you some overview of our lab other projects that working on it. So actually, I'm not working on it, but that's very interesting project that I think that it is worth to look at them. So this is for the autonomous navigation based on the perception-aware trajectory plan. It was of the most recent work with one of our graduate students. So I will show you the videos. And this was just showing that it doesn't use any like lidar, so just a vision based, but just for the drones, and we have a dynamic obstacles. So based on it, this is to try to see how we can still avoid this highly dynamic environment just using the vision and IMU information. And you see that it does just have the field of view of the camera is limited. It's not seeing all the scene, but still you can avoid the objects. And it's interesting that for creating these dynamic obstacles, use this specific object. It's like it's driven by drone. So the other row, actually, this is the drone that tries to avoid the collision with all these dynamics. And the last video is for the other one. Just showing this is one of the DARPA challenges that attended, and then showing interesting result that we have a LiDAR and IMU, and based on that, which, for example, sensor is more like reliable. Based on that, we can have a like fusion of the different sensing model in this challenge. So I leave you to hear it. selected. Nice. Selected. Nice. Yeah, yeah, that's the last video that I wanted to show. And yeah, that's actually the end of the talk. So I want to thanks especially to all of my advisors and all my collaborators over this time of my academia for this project, actually for this project, of course, but definitely the others, especially I would like at the end also special thanks to Professor Dr. Takirat, because Dr. Takirat is my first advisor and really helped me to actually starting this path in the robotics and motivated me a lot to pursue in the robotics area. So I still want to continue in this area. For your attention, and if you have any question, I'd be happy to answer now. And also, if you want to see Techno Lab, I encourage you to visit our page in YouTube. Thanks so much.
Thank you, Golas, for your very interesting talk. It was really informative, full of different aspects and projects. I'm sure that there are numerous number of questions here, at least from my student part. I'm sure that there are some overlapping research being carried out from our lab and your precious work during the past years. But we have limited time, about half an hour time. So up to this time, please, everybody who wants to ask questions, please raise your hand, and Mohammed will help you to turn on your microphone and ask questions.
Okay, can I add something?
Sure.
Okay, dear participants, please see your chat box and register your name to receive a certificate of participants in this webinar. And if you have any question, please raise your hands and I will help you to open your microphone to ask your question. Thank you.
I think Ali and Mahrukh have two of the audience have question. Please open microphone for Ali.
Stop sharing.
Okay, Ali,
yes,
please go ahead.
We still don't have Ali's voice. Try to open your microphone, Ali. All right, we can go to Mahrukh if Mahrukh, if you can open your microphone and ask your question.
Okay, hello, can you hear me?
Sure. Please, before giving your question, introduce yourself very shortly and then have your question.
Sure. My name is Mahrukh Hossein Khani. I'm currently a master's student in mechanical engineering under supervision of Professor Adi Ghaffari. I'm currently working on autonomous vehicle in highway off-ramp trajectory tracking using model predictive control. Already, if I want to say what I have done, I have used the model-based MPC, which uses like Newton laws, and you are going to use a lot of math. But according to the trend of the world of the technology, as you see that there are a lot of trends for reinforcement learning, I have made a collaboration with Norwegian University of Technology, NTNU, that we are going to implement MPC inside reinforcement learning. So I've got a question, actually a kind of asking an idea if Dr. Elnaz or Golnaz, I don't know her name fully, Habibi, yeah, Golnaz Habibi, yes. Yeah. I wanted to know, I was wondering if she'd mind letting me know that, is it possible to use the MPC inside RL, or better to say RL, or vice versa, better to say. Because when you have some rate on constraints, for example, I'm not going to so deep and complex and going through mathematics. I'm just going to speak so general so everyone can understand me. For example, in an autonomous vehicle, you are going to use your wheel, and you have some wheel angle, okay? But better to say steering angle as a command. But when you are going to tell that, okay, a dear car, you are not going to put so much angle at once for just, for example, one time stance, okay? You cannot, for example, 30 degrees just for just one input control increment. So you are going to make it 1 degree by 1 degree, a kind of, a rate on constraints. So the neural network inside reinforcement learning cannot do that, because you cannot, better to say, settle the weights of the neural networks to kind of satisfy the function that you demand from your car. So we thought that maybe we can put the nonlinear model predictive control inside the RL, so we can obtain the parameters better and with less effort, because that would be, I guess, that would be much more safe and that would be less computational. So I just wanted to ask that from your collaborations and things that you have done in MIT, have you ever heard, or have you ever thought about using some optimal control inside RL so you can gain your policies, your optimal policies by doing that? Because we propose to use RL to find these parameters. More specifically, RL used to tune the sequence of sigmas and then expected value from the noises and process noises and so on in order to improve the robust NMPC in RL. So I just wanted to know, have you ever done such a thing, or you are just using the pure RL inside your project? Thank you.
Sure. Yeah, thanks so much, Ms. Mahroh, about your interesting question. In general, there are a lot of arguments between, the classic control and learning-based control. So still, this is but the thing that I believe that we need both. So I really want to hybrid these two. Each benefits and leverage benefits of them. So, for example, some idea just it comes to my mind is one of them is, for example, for nonlinear NPC, there are some approach that they estimate based on, for example, we have some nonlinear NPC, but it's basically we collect some data and then either in simulation or real world, and based on usually in simulation, of course, that and using that to create, approximate by some neural network. And then when we have that, we can then combine this neural network maybe more easily if you want to use RL instead of just NPC. That's one thing, but in general, I see that also in reinforcement learning, they consider some of this constraint in the RL. I can send some references if you are interested on that. I'm not sure that which one actually is more computationally expensive, but we can think in both direction, either the one that you also mentioned, that is how we can combine it. The other point is about the reward function. We can also add there, in the reward function, basically, if, for example, your control constraint is higher than some, values that which is our limit, control limit, how you can, for example, get a very negative value for the reward function. And if it's in the range, so you have a better reward. So there are some different ways that we can consider it. But in terms of if you want to consider that constraint control in neural network or RL, I see some works on it, so I can definitely share with you later.
Thank you very much. That was very useful.
Sure.
Thank you. We can move on to Jawad or J. Moeen. I assume that it's Jawad Moeen, but please open the microphone. Jawad, Mr. Moeen, Mr. or Mrs. Moeen.
Hello, everybody. Yes, I'm Jawad Moeen. I have just recently graduated in mechanical engineering under the supervision of Dr. Nikopard and advising of Professor Taqirat. I have a question, Dr. Habibi. Have you ever considered uncertainty in your research and in your planning and navigation?
Yeah, definitely. I think I addressed some of them today. For example, we need to analyze the robustness of the network, robustness of usual neural network, in terms of the uncertainty, because usually the neural network is very sensitive to uncertainty or adversarial attack. So I consider that, and also in general for the for the RL algorithms, because more focus on the deep RL, but even in RL, classic RL, we have all this uncertainty. So it's actually the planning under uncertainty. So it just started, for example, with POMDP cases, and then today it's developed to the more learning-based and deep neural network-based RL. So do you have any specific question about that? I think you are mute.
Yes. I mean, uncertainty in your planning, motion planning, not in your, neural network. In, consider such as uncertainty in motion in a sensor or like this.
All this like the planning that we consider the uncertainty involved on it.
I guess in the first part of the presentation of Golnaz, it was more related with the uncertainty issues, both on the modeling, on the neural networks, and on the planning as well. Yeah.
Unfortunately, I wasn't. So thank you.
Sure.
Okay. You can go review the videos afterward. Paria, you're welcome. Paria, you have some question. Please unmute and give your introduction and then your question.
Hello, everyone. My name is Paria. I'm doing my PhD on RFID field at UKY, at University of Kentucky. First of all, thank you, Golnaz. It's wonderful presentation, and thanks to other guys that make this opportunity to be update ourselves and collaborate with each other. I was wondering, actually, I'm working on the same area, but in micro scale. In my research, I have a problem, which is maybe it's basic, but the first problem which we faced till now, it's a collision of a signal when you have a multi-signal, multi-object, especially when you have a multi-agent. I was wondering if you have this problem in your research or no, and if it's yes, how you handle it. Mm-hmm. Thank you so much.
Sure. This is a very, very good question, and nice to meet you, Paria. Actually, I didn't have a chance to talk about it today, but a part of my work was focused on how learning the communication protocols, specifically in the environment as for the multi-agent systems, and usually because we have this collision, the communications and the bandwidth limitations, so how we can learn the policy such that when to communicate and what to communicate, basically. So it's we learn it from some features from our graph of the network based on the, for example, network density, and also the existence of the hidden node problems, because hidden node problems, that's the other issue that we have usually in the Wi-Fi communications, and which make it sometimes that you cannot send a message because the channel is occupied with other agents. And that's why we focus on these two features, and basically we learn the policies. Again, we formulate it as RL problem, and then how we can actually plan based on that and have it the best policy, specifically for the task allocation problem, which is, for example, how we can allocate different tasks, task or different, for example, in case of for example, search and rescue problem, different, for example, survivors, or for example, people that needs the help among different agents. So there are some work I can also, if you have any specific question, I'd be happy to answer. Otherwise, also have a paper that I can share with you, our recent paper on that direction.
Perfect. Thank you, Golnaz. We can move on to Mohammed Mahdi. I would like to ask to shorten your question somehow, to have more question and answer available at the limited time that we have. Mohammed Mahdi, go ahead.
Hello, do you have my voice?
Yes.
First of all, I wanted to thank you, dear Dr. Habibi and dear Dr. Tagrat, to make this opportunity. I'm an ARAS graduate student, and I had a general question about your presentation in control field. One of the things you mentioned was the centralized controller, and I think the centralized controller has always its own risk of failure and other things, and how can we overcome this?
Yeah, actually, that's a good question. Actually, I am also more towards the decentralized controller. that's why actually decentralized and was born. I mean, because of the scalability and also the vulnerability that it happens for the centralized controller. Some of them that, for example, one of them that I showed that a specific example that for some specific problem we can still have a very low dimension of the control and sending like that massive uniform control that massive uniform control that we can send it. But in general, as we have more agent, we have that issue of the scalability and also how we can also control in general in a centralized fashion.
Perfect. Thank you, Gulnaz. We can move on to Saeed Bustan. If you can unmute yourself and introduce yourself and ask your question, please.
Hello, everybody. Hi. I'm Saeed Bustan, the PhD candidate in mechanical engineering, and my supervisor is Dr. Nahvi. I want to ask about as you know, the stability and transparency is a main problem in this size system. How do you solve these simultaneously?
The first one is transparency, but what do you mean there is a
transparency and stability, both of them?
Could you explain a little bit that in which sense transparency you mean? Because it's different meaning in different content.
I know, for example, we have, in transparency, you have the system that you have a real sensing in the body that is controlled. As you know, it's autonomous, but in some cases you may need for control that.
Control the sensing part, you mean?
Yeah, sensing, we have real sense in control.
The question is more the transparency between usually where we have multi-agent system or some multi-autonomous system, how they are transparently conveying the transformation to each other.
Okay. As I understand, you mean that how, for example, we can associate their data or fuse their data. Okay. Actually, that's a very good question, actually, also very challenging. So especially when we have multi-modality, we have different sensing, for example, Lidar, cameras, and many problems like even calibration, even a little bit, lack of the calibration within the sensing make it inefficient. And more classical way, they do manually calibration, but usually it's not very efficient in general, specifically when you have a moving object or mobile robots that all this, sensing can be changed, their position can change, and also over the time. So yeah, there are two different way of view. So it's like that mostly focus on the data association and also outliers. So they use a different algorithms, both based on the learning-based model and also classical model based on the spectral, for example, clustering algorithms. And based on that, they try to remove some of the outliers or noisy associations, so they can come up with a more robust and correct association between this, for example, different sensing modules. But it still is an area that people working on that and it's not finished yet. Yeah.
Thank you, Gulnaz. Yes. Yeah. We have maybe the last question, Mr. Saeed, if you can unmute, introduce yourself and then give your question, please.
Hi, can you hear me?
Yes, go ahead.
Yes, thanks for your great presentation. I actually have 3 questions, and I am pursuing my Master of Science in Structural Engineering at Sharif University of Technology. I have 3 questions. My first question is about how we can use the combination of GANs and semi-supervised learning in autonomous navigation. My second question is about what kind of
give one by one,
vision-based deep
please.
learning methods
I asked you to just give one by
mostly...
one. Said, just give one by one. Yes. The first question is multiple GAN and navigation.
My next question is about how we can, how we can use the combination of GANs and semi-supervised learning in autonomous navigation.
Okay. So do you have like more a specific question? Because like, as you know, for example, is it for example, a specific part of the autonomous navigation or in general? Because for example, like more, I think you were talking about the more part of the perception side of the navigation, right?
Yes.
I assume yes, because the GAN are using usually for that part.
Yeah. Actually, I'm not aware of. I can check it like if they do have this combination. Because I see that they're usually using the different way of thing, but it's actually GANs could help. It's kind of related to. It's not. It should not. I would not say that like they are like different from each other. It's kind of one of the way that we can do the semi-learning. It can be used GAN to help the network that without, for example, label data, how we can still have a good or few data, how it's still, because then we can, if we have a few data by using GAN, we can create like more realistic data sets and using that and augment it to your model to improve your learning, supervised learning model. So I would say this way we can combine these two together.
Of course, this is one way to use that. Okay, go with your second question, Saeed, but please short. We have only a few minutes left.
Thank you. Yeah, what kind of vision-based deep learning methods are mostly used in this field?
In perception, a lot of actually work today, and depends on what's your purpose and what's your assumption would be. So again, vision can be either just monocular cameras or astute cameras, and sometimes you have a combination of vision with lidars. And basically today is based on the deep neural network and then different architectures. For example, ResNet, one of the architectures that they use a lot, or also deformable convolutional neural network. That's the other one that used a lot today for the, for example, object detection and tracking algorithms. So it depends on like, and then they also combine it, for example, for the tracking side with some classical data association or learning-based data association to improve the tracking. So it's very dependent on the like your assumption and your application.
All right. If you can go with your last question, please.
Yeah, thank you. And about the heuristic and meta-heuristic application in this field?
That's a good question. I mean, it's still, I see that a lot of heuristic, approach there because of that. That's a problem of the lack of the interpretability of the neural network explainability. So in many cases that they cannot solve it just about neural networks. So they added, for example, in tracking side, adding the other module that, they combine different, output of a neural network or different similarity measurement for doing the data association for tracking side. So yeah, that's still a lot of work on that direction. I hope that someday we can have a better understanding of neural network and we can add this, add features that we can explain the output of the neural network, so we don't need to any like heuristic part to adding to that.
Yeah, hope for future. We still have a long way to go, although there are a lot of advancement in the terms of both in science and technology happening in this specific field, but still there is a very long way to go. I would like to thank you, Golnaz, again at the end of the session, and it was very interesting. Thank you for giving your time, your precious time to us, and we enjoyed, being aware of how well you have treated different field of control, and also navigation, the visual navigation, other means of research areas into very specific and useful applications. And this is we should expect from any Iranian, especially from ARAS alumni, of course, to have a very flourishing future. And I hope that you will find your career very soon, your way of career very soon, shortly. And we have more of your time and thoughts being shared with us during our webinar, public webinars. So if there is any final comments or anything that you would like to share.
Yeah, I would like to just again thank you again, Professor Taqirat, for giving me this time, and it was my pleasure to have a talk here. So, and also again, I'm very grateful that have you as my first and best advisor over my really all your serious advices and all your guidance, very helpful. I don't forget about that, and I hope that also I can continue more collaboration with ARAS in the near future. And thanks for everyone that attending in my talk.
Perfect. Actually, we have a group of students working on fusion of different modalities. Hamed and Ruhollah are both here, but I think I will give the time maybe in future to have more direct contact between you and this team to further collaborate or find some way of collaboration in the near future. I would like also to ask everybody who has some video, just give a few minutes at the last minutes of the session there, open their videos, and then we can have maybe a good picture, memorize. I see familiar faces here. The names are very difficult when you have a large number of names in the audience, but the videos are good. I still wait a few minutes to have everybody who has some camera. Of course, we are getting very close to Maghrib and Azan in the holy month of Ramadan. I wish everybody health and success, and I guess we can have, I can have one picture taken. Please smile. 1, 2, and 3. Okay, let me do another. Very good. I guess it is quite well. Thank you very much, everybody, for being with us. I would like to inform you that within 4 weeks, exactly at the same time, we will have our next alumni speech from University of Michigan. And that would be something related again to AI and robotics, but the poster and the approach will be given in the future. Please be with us, follow us on LinkedIn and on Twitter and other social medias, and hope you all success, health, and prosperity in this new year, Iranian New Year. Thank you very much, everybody, and goodbye.
Thank you so much. Have a good day.